Hello, and welcome to York Observatory's monthly TeleTube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alan I. Carswell Observatory located at York University in Toronto, Ontario, Canada. York TeleTube broadcasts every last Friday of the month at 7:30 p.m. local Toronto time right here on our YouTube channel. For any questions or comments you have about our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Instagram at the handle YorkU Observatory. We would like to inform you about the Summer 2026 Astronomer in Residence program. This program is a collaboration of the Alan I. Carswell Observatory with Killarney Provincial Park to host astronomers in the certified dark sky site of Killarney, to lead in-person presentations and shows using the park's observatory. To learn more about the program, visit our website at yorku.ca/science/observatory/AIR. Good evening, everyone. My name is Arthana, and I'm here alongside Shreya, Nakul, and Khalifa from the Alan I. Carswell Observatory at York University. We're excited to welcome you tonight and are pleased to host our guest speaker, Patrick Hall, who will be diving into an interesting topic of quasars. The observatory at York campus is in Toronto, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many Indigenous nations. The area known as Toronto has been caretaken by the Anishinaabe Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many Indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts join the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. Now I will pass the floor to Shreya.
Welcome everyone. As Arthana mentioned, my name is Shreya, and before we get started with our main show, we want to give you a little update on what you can see tonight. So tonight we'll be able to see Arcturus, which is one of the brightest stars we can see in the sky by our naked eye, and the star Vega and Sirius. The moon is in its waxing gibbous phase, and Jupiter will be visible a little west of the moon. You'll be able to see these objects except the moon by eye in the sky, but using a small telescope will give you the best results. Now we'll move on to introduce our guest speaker.
Hello, everyone. So for tonight, we have our guest speaker, Professor Patrick Hall. Patrick Hall is an astronomer and professor in the Department of Physics and Astronomy at York University. Born in California to Canadian parents, he double majored in physics and astronomy at the University of California at Berkeley and obtained a doctorate in astronomy at the University of Arizona. He then studied galaxies as a postdoc fellow at the University of Toronto and quasars as a joint postdoc at Princeton University and the Universidad Católica de Chile before joining the faculty at York University. His research focused on quasars, a supermassive black hole in a distant galaxy surrounded by accretion disk and high-velocity overflow of gas. He divides his work time between research on quasars, teaching, outreach, and administration. And right now, I would like to give it over to Professor Pat Hall for his presentation for tonight.
Thank you, Nicole, for that introduction. I will now share my slides and we'll get started. Meanwhile, you can enjoy photos of me up there. I think it's pretty easy to guess which one is the older photo. Okay, I'll start the slideshow. All right. So I'm going to talk today about quasars, which are black holes you can study, or that we, as humans and astronomers, can study from right here on Earth. So first off, the question, of course, is what is a quasar? Well, as far back as the 1940s, astronomers noticed that the centers of some galaxies were relatively bright, and they had very broad emission lines in their spectra. Now, I'm going to be talking a lot about spectra, which is just, as the slide says, fancy science jargon for rainbow. We take the light from an object, spread it out into different colors, and look at the emission, the amount of light at each color. And when we see an emission line that's very broad, as we'll see later, that broadening is from the Doppler effect, motion towards and away from us. So very broad emission lines means very fast moving gas. And scientists called these objects active galactic nuclei, or AGN for short. And a quasar today is just defined as a very luminous AGN. So an active galactic nucleus that puts out a lot of light. So here's an example of a galaxy below and to the left, and an AGN below and to the right. You can see in this AGN, it's a galaxy, but the center is very bright, and in fact, often outshines the entire rest of the galaxy. And if you move that galaxy to very large distances from us, you might not see the galaxy itself, but just the central part, the quasar. So that's what a quasar is, but what causes a quasar? Well, we can think of a quasar as a process, not a thing. So a quasar is what happens when matter spirals into a supermassive black hole through an accretion disk. And we can see in the background here an artist's impression of an accretion disk, which is a disk of matter around a black hole seen in the center. And matter spirals in through the disk into the black hole, but at the same time, the disk is expelling gas away from itself. So black holes do consume matter, but they're also messy eaters, and they throw a lot of matter away from themselves as well. So we've talked about quasars as being an accretion disk around a black hole. Well, what is a black hole? A black hole is quite simply an object whose escape speed is greater than the speed of light. If you toss a pen up into the air, it will fall back down because you haven't thrown it up at a speed of 11 kilometers per second, which is how fast you would need to throw it for it to escape the Earth's gravitational pull. And if we shrank the Earth down, its gravity would be stronger because we'd all be closer to the center of the Earth, and you'd need to throw the pen even faster than 11 kilometers per second. And eventually, if you could shrink the Earth down small enough to just a few centimeters, then you'd need to throw that pen faster than the speed of light to escape the Earth's gravity, and nothing can travel faster than light, so nothing can escape a black hole. So objects can orbit a black hole. That's not a problem as long as they're moving fast enough. But the closer you get to the black hole, the faster you need to move to stay in orbit. And if you get too close to the black hole, within a few times the radius of the black hole, then no stable orbits exist. But if the sun became a black hole, the Earth would continue in its orbit, and the orbit would barely be disturbed. So if you, however, get close enough to the black hole to get within what's called its event horizon, you won't be able to escape. And if a black hole is not spinning, the event horizon is located at what's called the Schwarzschild radius, named for Karl Schwarzschild. And I held off on showing you his photo because I didn't want you to be distracted by that mustache of his. So Karl Schwarzschild worked out the distance at which a black hole, or the size of a black hole, let's say, and we now name that distance the Schwarzschild radius in his honor. So that's what a black hole is, but do we actually have evidence for a black hole? Yes, we do. In fact, we have evidence that every massive galaxy has a central black hole. And how do we know this? Well, the best evidence we have is at the center of our own Milky Way galaxy. There's an object called Sagittarius A star. It's a source of radio emission, and we can actually study the orbits of stars around this object. And Dr. Andrea Ghez, Nobel laureate, has done that with her group at the University of California, Los Angeles. And they and the other group studying Sag A star find that it has a mass of 4 million suns. So let's look at the little animation they produced. Here are a bunch of stars with, let's go back there. There we go. Here are a bunch of stars around the black hole, and let's watch them orbit. So top right, you see the year, and you see stars are plunging close to the black hole and moving faster as they get close to it, and then moving slower as they get away. And we're continually improving our resolution, but by studying how fast the stars move as a function of distance, we can work out that there's a black hole of 4 million times the mass of the sun at the center of our Milky Way galaxy. So I've told you that a quasar is a black hole surrounded by an accretion disk, and we've talked a little bit about black holes, and even that every massive galaxy has a central black hole. But does that really matter? Well, it turns out it does. Most black holes are not accreting a significant amount of mass right now, but in order to get as big as they are, millions or even billion times the mass of the sun, they must have been pulling in matter in the past. And when they pulled in matter, they were also producing powerful outflows because they're messy eaters. And those outflows affected the surrounding galaxy, eventually shutting down its growth, as well as the black hole's growth. So it turns out that black holes matter quite a bit for the formation of massive galaxies. If black holes didn't exist, then massive galaxies would look a lot different than they do in this universe where black holes do exist. So we'll see that through a galaxy formation simulation by these three astronomers here. What they did was they studied two disk galaxies coming very close to each other and merging, and the effect of that merger on the galaxy's gas. So the animation I'm going to show you doesn't have any stars in it. It only has two disk galaxies full of gas. And so we'll see that the gas is eventually used up and ejected, but remember, the stars are still there. Okay, so here we have two disk galaxies. At closer to the center of the galaxy, the gas is orbiting faster, and we can see spiral arms forming. That's a natural thing in disk galaxies. And now the galaxies are colliding, and those redder colors indicate hotter gas. And so you can see there's where the galaxies collide, there's hotter gas, and gas is now starting to flow into the centers of these galaxies where there's a supermassive black hole. And you'll soon start to see the effects of the quasar's messy eating as gas starts to be heated up and ejected. As gas flows into the black holes, there we go. Now you're starting to see gas ejected from the quasars. As the quasars are fueled by gas, they also expel a lot of hot gas, and that hot gas drives out the remaining cool gas. And eventually, we'll soon see that in a merger of these two galaxies, almost all the gas is blown away. So either the gas forms stars, or it's blown away by the quasar at the center of this single galaxy that results from the merger of two galaxies. And we're left with what's called an elliptical galaxy, a galaxy with no gas left and with only old stars because no more stars are forming. Okay, so let's go back to talking about quasars. I hope I've convinced you that they're important and they help form galaxies into the galaxies we see today. So a quasar is a black hole plus accretion disk. So the closer you get to a black hole, the faster you need to move. And as a cloud of matter approaches a black hole, it will be stretched and torn apart by tidal forces, which just means that the gravity at the side of the cloud closest to the black hole will be stronger than the gravity at the side farther away, and that will stretch out the cloud. And as it gets stretched and torn apart because it gets too close, it will end up as a flattened accretion disk. And a quasar is just a black hole plus accretion disk plus the winds that come off the accretion disk and occasionally jets as well. We won't talk about jets much today. So the accretion disk is what gives off the light we see. So an accretion disk is modeled here from the movie Interstellar, which is well worth seeing. And Interstellar consulted with Kip Thorne, professor at Caltech, to get a good picture of what an accretion disk would really look like. So you can see the black hole in the center there, and you can see a disk, and you can also see a ring. That ring is the accretion disk multiply imaged is the technical term, Gravitationally lensed is another way of saying it. The gravity of the black hole is actually letting you see the top and bottom of the accretion disk and the far side of the accretion disk at the same time as you're seeing the near side. So gravity is just distorting the path the light takes from the accretion disk. But physically, that's a circular disk surrounding a black hole. Okay, so let's go back to this accretion disk. You can see it in the center there, glowing very hot at the center, because as matter spirals into the black hole through the accretion disk, it heats up basically through friction. And different distances from the black hole glow at different temperatures. So at very small distances from the black hole, the gas is moving very fast. There's a lot of friction that heats up the gas to very high temperatures, and it becomes hotter than the surface of the sun. Farther away, the gas isn't moving as fast, and so it can be cooler than the sun. And so this accretion disk can emit as much light as 10 quadrillion suns. You can see all the zeros there in that number. And the ultraviolet light launches an outflow from the disk. So what would an accretion disk structure look like, or what might it look like? Well, here's some Canadian content from two astronomers here in Canada. This is a cross section. This is a cross section of an accretion disk. At the center, there's a black hole. You can see the accretion disk there. And the idea is that near the black hole, the gas is very hot and producing X-rays. Those X-rays are absorbed by this shielding gas. And then beyond the shielding gas, a wind can be accelerated by ultraviolet light. And that wind forms what we call a broad absorption line wind. And that's what I study. So where do we get the data that we've concluded all this information about quasars and black holes that I've told you about? Well, most of my models are based on data from the Sloan Digital Sky Survey. It's currently in its fifth iteration, using a 2.5-meter diameter telescope in Apache Point, New Mexico, and a 2.5-meter diameter telescope in Las Campanas Observatory in Chile. So we're observing quasars all over the sky in SDSS-5 right now. SDSS started with a survey of 25% of the sky in 5 different wavelengths of light. And since then, it's obtained spectra, those little rainbows, of over 1 million stars and galaxies and over 500,000 quasars. And it's now in its 5th phase, as I mentioned, obtaining spectroscopy of quasars and known quasars, that is, and quasar candidates. So how do we do this? Well, at each telescope, we take optical fibers, and you can see in this image here in the center, little optical fiber. We place these optical fibers using these little robots shown here in the precise positions needed to capture light from specific targets. And that light has been traveling to Earth for thousands of years for stars, millions of years for nearby galaxies, or billions of years for distant quasars. And since 2020, we've been using 500 robotic fiber positioners at a time, but we have a competitor survey called DESI, which uses 5,000 robotic fiber positioners. And probably in a decade or two, there'll be telescopes using 50,000 fibers at a time. So with all these spectra we obtain, we're able to study the emission and absorption properties of quasars. So from an accretion disk, we have light at a whole bunch of different wavelengths, a white light source. So this source is brighter at short wavelengths, so it looks blue, and it has emission lines with gas traveling at about 10,000 kilometers per second due to the Doppler shift. And about 1 in 4 of these quasar spectra have broad absorption lines from outflowing gas. And that outflowing gas can reach speeds of up to 30% the speed of light. So here's plots of spectra that I'm going to show. On top, there's an average quasar. And what I'm plotting is, again, a little rainbow. I didn't have a chance to color code it. But on the left, that's blue light. And on the right, that's red light. And higher a higher position in the plot means brighter. And so at short wavelengths, blue wavelengths, there's more light than at red wavelengths. So this average quasar looks blue. A broad absorption line quasar has the same blue shape, plus broad emission lines, but it also has absorption lines. And then we can find some Bow quasars which are reddened by dust and look, in fact, quite red. So these blue shifted troughs are absorption from gas traveling away from the quasar and towards us. And that's by the Doppler shift. So here's the Doppler shift. Earth is here on the right, and we have three objects emitting light at the same wavelength. So the middle one is emitting light at a yellow wavelength and is not moving relative to Earth, so we see that light as yellow. But if an object is moving towards us, if it's emitting at the same frequency, going up and down at the same rate, that light is seen by us as blue. And on the bottom, there's an object moving away from us, but moving up and down at the same rate, but we perceive its light as red. So we can use the Doppler shift to tell whether gas is coming towards us or away from us. And that helps us study quasars as well as lots of other things in the universe. So what strange and wonderful quasars has the Sloan Digital Sky Survey found? Well, I'm going to tell you. So the latest exciting thing that we've just had accepted in a paper to a peer-reviewed journal is what we call a new member of the Fast and Furious family. Most of the outflows we see in quasars have velocities less than 10% of the speed of light, or 0.1 c. There's a subset that have velocities at greater than 0.1 c, but we've just spent time in my group looking for faster and faster outflows. In 2016, we found one that was 20% the speed of light with my former student, Jesse Rogerson. And just now, we've broken the record for the fastest extremely high velocity outflow discovered in the ultraviolet and tying for the fastest overall outflow seen in the ultraviolet, 30% of the speed of light. So this uses data from SDSS, and here it is. Here's another spectrum. This spectrum is somewhat different looking, but it's the same idea. Long wavelengths on the right, short wavelengths on the left, and these two arrows show where the absorption trough is shifted from. The absorption, if it wasn't moving towards us, would appear here, but it's shifted to shorter wavelengths by the Doppler effect, shifted bluer by 80,000 kilometers per second on average and 90,000 kilometers per second maximum, which is 30% of the speed of light. So that's one of the interesting things. This object was found by a former undergraduate student, Mariana Veltri, just by looking at spectra of quasars from the SDSS. And also just by looking at quasars from the SDSS, I found and recognized an unusual set of broad absorption line quasars where the gas appears to be moving away from us. And that may not sound surprising because gas moving away from us toward the quasar, well, isn't that gas just feeding the quasar? That was an idea we had, but it doesn't quite seem to work. This spectrum here shows absorption at red wavelengths relative to emission lines, not blue wavelengths. And we think that's due to us seeing gas in rotation very near the black hole. So here's an accretion disk illustration, and the blue and red arrows show the velocity of gas launched from the accretion disk in a rotating wind. And we can actually see red shifted absorption, gas moving away from us just above the surface of the disk just after it's launched. And so if in some cases we only have gas moving away from us and not gas coming towards us because the wind is patchy, then we think we can explain these red shifted trough BAL quasars. But there's still something I'm studying actively. So here's an object which my student last summer, Giuliano Di Nuno, studied. It's not actually a broad absorption line quasar. It's an object with blue shifted emission. So again, on the left is blue light, on the right is red light. This is the detailed fitting that we do to understand these quasars. You don't need to worry about that. Just on the top, you can see there's a bunch of emission lines. And this one here shows you that emission is starting here, and then there's lots of blue shifted emission, out to about 7% the speed of light, which is pretty much tying a record. This quasar with this much blue shifted emission is very unusual. So we'll be working on that some more this summer. Another object is called JO230, and all these numbers just indicate position on the sky where if I gave you the full coordinates, you would know where to point your telescope to see these objects. This object is the third fastest ultraviolet BAL quasar, and you can see at different times it has absorption at different wavelengths. They're moving around in a way we're not quite sure we understand yet, and Arthana will help me try and understand it some more again this summer. And there's yet another BAL quasar where it has some normal BAL troughs that are just coasting at fixed velocities, plus one trough that's accelerating. So again, short wavelengths on the left, meaning a blue shift. At the center of this plot, there's some absorption, which stays in the same place over time. That's gas, which is just coasting at a fixed velocity. But there's also a component of gas, which is moving to shorter wavelengths, meaning it's accelerating. So we're not quite sure exactly why one trough is just coasting and the other is accelerating. There must be some difference between the troughs, even though they both produce weak absorption in the quasar's spectrum. And a few more just to show off how much SDSS is providing for lots of different students here at York to study. This is a quasar which is slowly getting less dusty as seen by us. When it was looked at many years ago in the Sloan Digital Sky Survey, it had this bottom spectrum. And then later on, it was observed by our competitor DESI, and it's brighter and bluer. So that means there's dust between us and the quasar, which is gradually moving out of the way, or at least that's the simplest explanation. And we'll be seeing if we can test that and see if maybe some more complicated explanation is needed, like there is for this object. So this object is a quasar which got dustier. So at first we thought, oh, there's just gas with dust moving between us and the quasar, as the quasar got fainter and redder. But now we've learned that the quasar has gone back to being bright and blue. So either a gas cloud moved between us and the quasar really quickly, which we don't think it can actually do. It's moving a little too fast for that explanation to work. Or dust sort of formed between us and the quasar and then was destroyed. And so this might be like soot forming in a fire and then dissipating. But again, it's something we're studying more. And last but not least, I just wanted to put up a random BAL quasar. It's kind of noisy. On the left, there's lots of flux missing. That's being absorbed by gas between us and the quasar. And this was one of hundreds of quasars that I and others identified using SpecViewer, which Zhezhou Zhou has worked on for the past couple of years working with me. So in conclusion, I'd just like to say that Canadian Astronomy thanks you for supporting us, not just the Sloan Digital Sky Survey, but all kinds of different telescopes. The Gemini North Telescope, which was used for one of the quasars I talked about today, and lots of other telescopes in use at the moment. So I'll stop there and take questions. Thank you very much.
Thank you, Professor Hall, for the very insightful presentation, and I am indeed quite excited to continue researching on JO230. We really appreciate you sharing your time and knowledge with us tonight. And for those who may have questions about the talk, please stay towards the end of the live stream to ask your questions via the chat. And the co-hosts actually have a couple of questions, so I can start off. So, my question is, so recent observations from the James Webb Space Telescope have revealed these objects called little red dots. So, how could studying these objects improve our understanding of quasars as they evolve in the early universe? And how do they differ from the high redshift quasars we already know about?
It's a good question, and I actually have some slides prepared on this, so I'll go ahead and share my screen again.
Mhm.
So JWST, for those who don't know, is a space telescope, and one of our professors at York, in fact, got the largest ever allocation of time on JWST in the previous proposal round. So it works in the infrared, and its diameter gives it an ability to see very faint objects and very sharp images unaffected by the atmosphere, which is why we can use it to study objects when the universe was less than 1 billion years old. And these little red dots are objects that we now think are unusual kinds of quasars. So here's a spectrum of a little red dot. And if you look at only the left-hand part, it looks kind of like a quasar. Again, this is short wavelengths on the left, long wavelengths on the right. And so just like a quasar, in the left half of this plot, there's more flux at short wavelengths. That just means the object looks blue. And there's even this emission line from Lyman alpha. That's a common strong emission line in quasars. But then there's something else is going on at longer wavelengths. There's this reddened component, which makes for a V-shaped spectrum. And so that's very distinctive. There's very few objects that look like this at low redshift. And so what we know about little red dots is that they're not resolved by JWST. There's a few that are resolved, but we think most of the flux is unresolved. Let's put it that way. So they must be physically small. They're red due to high redshift and this spectral break from hydrogen absorption. So if I go back a slide, this dip is caused by excited hydrogen absorbing photons from the object. And they have broad emission lines. So we think that's from gas around black holes, but they don't have X-ray or far infrared detections like normal AGN. So for a while, people were thinking maybe these were ultra dense galaxies, but then we realized no, that they'd have to be so dense that stars would be colliding and you'd see X-rays from that. So now the best idea for these objects is called the black hole star idea. So if the black hole is accreting at an extremely high rate, then the disk that starts to form will actually puff up. And when it puffs up, it can puff up so much that it's basically a sphere around the black hole. So if you just dump too much mass around a black hole, too much gas, then the photons will try to escape, but at the same time they're trying to escape, the gas is spiraling into the black hole, and the gas can spiral into the black hole before the photons can escape. And so, or at least before some of the photons can escape. And X-rays and UV photons from very hot gas, they get converted as they make their way outwards to lower energy photons. So you start with lots of photons of all wavelengths, but the dense gas atmosphere absorbs everything below about, essentially it absorbs all ultraviolet photons and only optical and infrared photons escape. So this is very exciting because it's implying that many, or at least some quasars, maybe not many, maybe not all, but at least some quasars accreted gas at a very high rate when they were young. And so we need to understand that if we're going to understand how quasars form. And it's worth pointing out that little red dots were not predicted. No one predicted that these things would exist. So it's very exciting to get this insight into the early lives of quasars that we didn't know about before. I hope that answered your question, Arthana.
Yes, it definitely did. Thank you for answering that. So we can go on to my next question. How do magnetic fields and a black hole spin play a role in a quasar's ability to create and sustain a relativistic jet?
Another good question. As you can see in that little image there, this is a radio galaxy or quasar, the little white blob in the center. And then the reddish blobs are a relativistic jet, those two narrow, thin threads. That's gas moving away from the quasar in opposite directions at almost the speed of light, and then plowing into gas in the surrounding intergalactic medium and slowing down and producing lots of radio waves. So we think, although it's not my area of expertise, that this is due to magnetic fields, which essentially are caused by electric currents. So this is a snapshot of a simulation of an accretion disk around a black hole that produces relativistic jets in opposite directions. So as charged particles get close to the black hole, they're moving faster and faster, and they can create and amplify magnetic fields. And the black hole itself is probably rapidly spinning, or at least is in some cases. And it's actually possible to extract spin energy from that black hole. So electric currents in the disk create magnetic fields, which extract energy from the black hole, and that energy helps drive particles away from the black hole along its spin axis in opposite directions at nearly the speed of light. And they're guided by these magnetic field lines. You can think of this as electric current that creates a magnetic field around it. So it's not completely understood exactly what's going on. There's some evidence that some black holes with jets are spinning slowly. So maybe a rapid spinning black hole helps create a jet, but maybe it's not absolutely necessary. Maybe more massive black holes are also able to create jets. So I think its black hole spin helps create a jet, but may not be absolutely necessary. Magnetic fields, however, are definitely necessary to create and keep a relativistic jet running.
All right, thank you very much for answering both my questions. We will move on to the next couple of questions.
Hi, Professor Hall. Thank you so much for your presentation. And so one of my questions is that what is one misconception students usually have about quasars that you wish more people knew about or kind of just understood?
I think the main misperception is not about quasars as such, but about black holes. And that's that black holes just pull in everything around them. That's not necessarily true. As I mentioned, I think in the talk, if the sun turned into a black hole, which we definitely don't want it to, and it wouldn't, so don't get worried. But if it did, the Earth's orbit would barely be affected. The Earth is far enough away and it's moving at the right speed so that if we suddenly orbited a black hole with the mass of the sun, very little would be different about Earth's orbit. If you got close enough to this new black hole sun, yes, then you could in fact get so close that you would not be in a stable orbit and would need to continuously fire your rocket engines to stay in orbit. And then eventually you'd run out of fuel and you'd fall into the black hole unless you've had enough fuel to get farther away from the black hole again. But by getting very close to the black hole and then getting far away again, that's how particles can extract spin energy from a black hole. But the basic misconception is that a black hole pulls matter in. It doesn't pull matter in. It's just a source of very strong gravity. And if you get very close to it, yes, you can be pulled in, but that's only about 6 times the radius of the black hole. So if you stay more than 6 times the radius of the black hole away from a black hole, you'll be fine as long as you're in a stable orbit.
Yeah, I completely agree with that. When I was little, I used to watch these videos and read books, just like children's animations or children's books. And they would kind of show that black holes suck in things, which is obviously not correct. So I think yeah, that's definitely a great answer for that question. Um, and my next question I have for you is that if a quasar's luminosity exceeded theoretical limits for sustained accretion, what explanations would you consider first?
Well, I wouldn't be worried about this at all because the theoretical limit for sustained accretion is for a very simple case of spherical symmetry. So that if a black hole was absorbing or attracting matter from in every direction in the same amount, then you can work out, well, how much matter could it accrete before the light it produced would push away the matter and exactly balance its own gravity. But as we've seen with this discussion of accretion disks, quasars are not accreting spherically symmetrically. So a way that you can exceed this limit for sustained accretion is just that the matter comes in the plane of the accretion disk, and the photons produced by the matter travel away in the polar directions of the accretion disk. So matter is coming in, and the photons are traveling away in different directions. And that way, the matter can keep coming in without being pushed away by the light created by the friction and heat of the matter spiraling into the black hole. So it's quite possible, and we've seen in some systems in our own galaxy of stellar mass black holes or neutron stars, that you can accrete up to 100 times the theoretical limit, just because, again, the matter's coming in one direction and the photons are going out in the other. So the photons aren't pushing away the matter that's trying to get in.
Yeah. Thank you for your answer, Professor Hall.
Hello, Professor Hall. Based on the topic on quasars, I have two questions for you. And my first question is, what happens to the black hole when two quasars collide?
Well, in that simulation I showed where two galaxies with black holes at their centers collided, it's not a simulation that makes it easy to see what's going on with the black holes at the centers, but they are getting closer to each other, and they will eventually spiral into each other and collide and form one supermassive black hole. And this is a bigger version of what's being detected by the LIGO gravitational wave observatory. That detects what happens when two black holes produced by dying by stars which have died collide. So as two black holes get close to each other, they're distorting space and emitting what we call gravitational waves. So they're actually losing energy to radiate these gravitational waves. And that loss of energy means they get closer to each other, and that means they lose more energy. And so this runaway process leads to a merger and a signal in gravitational waves that we've detected from stellar mass black holes colliding and merging. And there's a proposal to build the Laser Interferometer Space Antenna, or LISA, that will actually detect mergers of supermassive black holes throughout our universe. And in fact, we think we have evidence from the timing of radio waves from pulsars that there is a background of gravitational waves from these mergers. So you can think of LISA as detecting the sound of individual black hole mergers, supermassive black hole mergers, I should say. But we've already detected, we think, the sort of background hum of all of these merging supermassive black holes occurring over time in our universe. Hope that answered the question.
That's awesome, Professor Hall. Thank you so much. And my next question is, if the Milky Way's black hole accretes a large gas of clouds tomorrow, would we become a quasar?
If the gas cloud was massive enough, yes. If it fed enough mass into the black hole at the center of our galaxy, yes. The 4 million solar mass black hole at the center of our galaxy, though, is a little puny for a quasar, so you need a very large amount of gas, but it could happen. And it may have happened in the past, but more likely is that in the past, the Milky Way has been an active galaxy and will be at some point in the future. But I kind of doubt that the Milky Way has ever been luminous enough to be a quasar. But it could happen.
That's amazing, Professor. Thank you so much for answering the questions. And I will pass it over to Khalifa.
Hi, Professor. My first question is, are you able to see and identify a quasar through a telescope, or is it difficult to observe, like a black hole?
Yes, we can see quasars through telescopes. for black holes, we can't see them directly, but we can see the shadow of black holes. So the Event Horizon Telescope has seen the shadow of two black holes. And quasars, because we're seeing the accretion disk and not the black hole itself, that's easy to see because the black hole, excuse me, the accretion disk can be bigger than our solar system and brighter than the surface of the sun. So it shows up in surveys, sometimes like this. I'm sharing my image now. This is the twin quasar. It was the first gravitationally lensed quasar discovered. So these are two images of the same quasar, where the reddish blob between them is actually deflecting their light, acting like a lens and sending light in two slightly different directions, and such that we see the quasar, we see the quasar appear to be in two different directions on the sky, but it's actually light from the same quasar. And you can see this quasar is bright and blue, and so it's quite easy to see in surveys like this one of the night sky. Hope that answered the question.
Yes. My next question is where s- where do supermassive black holes that form quasars come from?
Yes, another good question. So these supermassive black holes, they could come from anything, any matter that goes into a black hole will add to the mass of the black hole, and the mass and spin of the black hole are the only things that we worry about. But we think that these formed from the mergers of smaller black holes. And so you can say, well, where did those black holes come from? And it comes back to the fact that if you're a star of 10 or 20 times the mass of our sun, then when you reach the end of your life, you will collapse, and the center of a star more massive than about 8 or 10 times our sun is too massive to form a neutron star. It actually forms a black hole. So the star, when it reaches the end of its life, it collapses, and that collapse isn't stopped by anything. It just, the star collapses and forms a black hole. So lots of 10 solar mass black holes are expected, and some of those black holes are in binary systems. So two 10 solar mass black holes can then merge, and then you've got a 20 solar mass black hole. And at the centers of galaxies, there's lots of stars forming. And so that 20 solar mass black hole can find another 10 solar mass black hole, and then you've got a 30 solar mass black hole. And that goes on until you build up something like the center of our galaxy, where it's 4 million times the mass of our sun. And in more massive galaxies, you can reach up to 10 billion times the mass of our sun. So 10 billion times the mass of our sun means that there's probably a billion stars worth of black holes that have merged to form that supermassive black hole. Now, in reality, it was probably fewer stars and then a lot of gas that got uh, accreted onto the black hole, but still millions of massive stars forming black holes, and those black holes merging together to form a supermassive black hole is where we think those black holes came from that allow us to see quasars. So I hope that answered the question.
Yes, thank you for that answer.
I don't
You
know if
have
we,
been,
sorry, go ahead.
oh, sorry, I think I'm just gonna do the outro now, or
Well, let's check and see if there are any questions on YouTube that Arthana or Nakul have spotted and can relay to me.
oh, okay.
I'm happy to answer questions if there are any. And I don't think I had any other slides to share, but I can if we have a good question.
Sorry. We can wait for about 2 minutes. Just I'm looking at the live chat right now, and then we can do the outro.
Okay, sounds good.
Okay, sounds good.
Okay, so someone did ask a question from Siddharth. They asked, what would happen to a galaxy that would encounter the relativistic jet coming out of a quasar?
Hmm. Good question. And in fact, in my thesis for my PhD, I in fact found evidence of that actually happening near a quasar. So the relativistic jet is relatively small and doesn't actually have a lot of mass, but it's moving so fast that when it hits a galaxy, if that galaxy has any mass in gas, that gas will be shock heated. So if there's, for example, let's just say the Andromeda galaxy started forming a quasar with a jet that was pointed towards the Milky Way and pointed towards the sun, that jet would look to us like a very bright source of light at all these different wavelengths. But the jet passing over the solar system, I don't think it would be, it wouldn't be too dramatic. It might produce more background radiation than we have right now, but I don't think it would be that big a deal. But if that same jet hit, let's say, the Orion star forming complex not too far away from us, the gas in the Orion Nebula would be shock heated and it would be pushed away. And that would mean that the star formation in the Orion Nebula would pretty soon come to an end. So the relativistic jets are one way that quasars shut down star formation in the galaxies around them. They don't really affect the stars because the stars are, solid, and so gas hitting them is not a big deal. But gas clouds are pretty tenuous, and so relativistic gas hitting a gas cloud would be pretty destructive. I'd have to check the numbers to be sure, but that's my impression, is that it wouldn't be too big a deal for the sun, but it would be a big deal for a star forming cloud to be hit by a relativistic jet. And it's rare, but we do see relativistic jets hitting nearby galaxies in a few cases. So thanks for that. Good question.
I'll wait about a minute to see if we have any more questions, and then Khalifa, you can go ahead.
I'll just share my thank you slide again for a minute or two, because I did want to mention the proposed Castor telescope, shown here at the bottom right, the Cosmological Advanced Survey Telescope for Optical and Ultraviolet Research. This is a Canadian-led proposed telescope that would monitor active galactic nuclei and other things from space in the ultraviolet as well as the optical. So the James Webb Space Telescope is great, but it doesn't observe in the optical like the Hubble Space Telescope does. And the Hubble Space Telescope won't be around forever. So we're hoping to get the Castor mission approved and built and launched and working to study the universe from space at ultraviolet wavelengths.
All right, I don't see any more questions. You can go ahead, Khalifa.
Okay, you have been listening to the Allen I. Carswell Observatory's monthly TeleTube broadcast brought to you by the Astronomy and Astrophysics program, which has been written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening were Arthana, Shreya, Nakul, and Khalifa. All of our programs are free, but if you'd like to donate, see our website at yorku.ca/science/observatory. You can always connect with us on Pixelfield with the handle at York Observatory, and check out our website for show notes, content updates, and contact info. Thank you for tuning in. Clear skies and have a good night.